Okay, so I'm not going to sing, thank God, but I'm going to run through something more specific about my research group. I'm not going to talk about our Great Salt Lake stuff. Instead, I'm going to talk about particle transport. That's me doing paleomagnetic stratigraphy when I was doing my master's thesis way back when. And this is Mohammed Khan, who was my protector. This was in Pakistan. And while I was there, I made some other friends. And they got me interested in particle transport and force movement. And what you need to know about that is that as a population of bacteria or particles moves through sand or gravel, for each layer of grains, you remove a fraction called eta of the population. And as you move through layers and layers and layers of grains, you have compounded loss that results in the concentration of particles decreasing about linearly with distance. That's true, though, if they're oppositely charged. And those are conditions favorable for attachment. In the environment, that's not the case. All surfaces tend to be negatively charged, they repel, and so you get these non-log linear decreases that make it impossible to predict how far things get in the environment. And so when we go to the pore scale, to the grain scale, to understand this better, we model the forces and torques acting on particles, and we determine whether or not they attach. And they will not attach if there's repulsion. So what we have to do is invoke heterogeneity at the nanoscale, which we know exists, but it's hard to get at. And so we paint surfaces with different sizes of clusters of heterogeneity, different surface densities, and we find that colloids or particles can either attach very quickly or very, very slowly. And when we upscale those, that is when we compound those, we actually, these curves emerge from that information at the pore scale. We actually get these non-log linear profiles, but only if we assume that these fast attaching particles aren't replenished during transport. And that's an unconventional assumption. So we've developed this hypothesis that incomplete mixing at the pore scale actually prevents that replenishment. And tracer studies show, if you represent the tracer in black and pure water in white, the invasion of that black water isn't complete, right? There's incomplete mixing that creates fingers. And the zones of incomplete mixing actually propagate from the rear sides of these grains. And that's where we see the simulations put all the particles that don't attach. So we're looking at those pore scale simulations to understand what's happening at larger scales and in the field. So I like to also take other people out to exotic places and to see if they get sick, which most of them do, actually. And so this is in Ecuador, mining impacted streams that we studied there. This is us crossing the Nangaritza River in an unconventional way, hanging out by a waterfall. And then last June, I took Owen Kahn, Sam Carter, Richie Torney, and Kerry Marshall from Geography up to the Himalayas of India, and we sampled water supplies in small villages and monasteries up there and had a great time. And found that it was really hard to sleep at 14,200 feet, actually. So that's it.